Good afternoon, folks. Today we are going to discuss benefits of ground improvement system for above ground storage tanks. We will briefly discuss about types of storage tanks, design challenges, performance criteria while designing these m- large diameter tanks, and traditional foundation support we designed to support these structures. Then we'll talk about brief overview of ground improvement technologies. We'll learn about advantages and benefits of using Geopier systems to support these tanks. And in the end, I will present four case studies where we have successfully used Geopier technologies to support these tanks and meet owners' performance criteria. Mainly, we can categorize storage tanks into two categories like above ground storage tanks and underground storage tanks. Underground storage tanks are generally embedded about 8 to 10 feet below the ground, but today's discussion is focused on above ground storage tanks. There are several types of these storage tanks, and what we're going to consider today are large diameter storage tanks, what you see on the upper right hand side, where about 200 feet diameter steel tank which is typically supported on granular pad or ring wall foundations. The flexible floor system of the tank generally has some asphalt or sand underneath for containment reasons. Then we can also talk about, we are going to talk about some LNG storage tanks, horizontal bullet tanks, what you see on the lower right hand side, and in the end we'll consider case history for elevated water storage tanks. The elevated water storage tanks, you see three different types in the lower bottom side of the screen. These tanks exert heavy loads and they're typically designed to for about half mega gallon to 2 mega gallon water carrying capacity, and they are generally the overturning moment governs the design, and the foundations for these tanks are generally um, ring wall foundations embedded about 5 to 6 feet or sometimes 10 feet below the ground. What is the purpose of these tanks? And these tanks are generally used to store crude oil, petroleum products, chemicals, or hazardous materials. And so it is extremely important that we follow all the API, American Petroleum Institute, and EPA guidelines while designing these structures. Let's talk about design considerations that need to taken into account while designing these structures. These tanks are typically 100 feet to 300 feet in diameter, and they are 40 to 60 feet in height. The pressures exerted on the foundation soils from these tank structures vary anywhere between 3,000 to 6,000 psf. And because of the footprint of these tanks, the pressures even at 40 to 50 feet below the existing ground or below the bottom of the tank, the pressure dissipation is very slow. What it means is if you have 5,000 psf acting on the below the tank bottom, about 30 to 40 feet below the tank surface, the pressure delta P is about 4,500 psf. So if you have any soft clays, loose sandy material, even a 5-foot thick layer can cause considerable deformation, which can lead to the settlement of these tank structures. When you see tanks, you see what next thing you see is pipe racks. So these pipes are connected to the tanks. If any there, all those these piping connections are flexible. Sometimes they are not, and what could happen if there is too much tilting or distortion of the tank, the welds can break, and that could be an issue in functionality of these tanks. How about shallow groundwater conditions? As you see in the pictures, most of these tank farms are located to the water body. So it is clear that water is shallow at these tank farms, and considering the EPA's regulation, we got to be careful while designing the proper foundation system which will not contaminate the groundwater conditions. Adjacent constructions, when these tanks, when you see two tanks in 2015, after 5 years you probably owner or the tank refinery wants to build five more tanks, and as the footprint or real estate with these tanks increases, you need to be careful considering the overlapping stresses that the foundation adjacent to the proposed tank locations. Duration of the construction. So as I said, these tanks store material which are petroleum hazardous. There is fleet of work going in background. So duration or erection of this tank, the overall construction period is very tight. If the tank is not ready, we cannot store the material. So we really need to consider and properly manage our projects to meet the milestone dates of the construction. API code and EPA requirements. Due to the nature of the material stored, these are the critical structures, and we need to study the containment area. Sometimes these tanks are double wall tanks, or they have some containment berms, and we need to consider this in the design. What happens in the field? Site history. As you know, good site to hard to find, we need to know this where these tanks will be constructed. What was that site? Was it a dredge fill site? Was there any previous structures present on this site? How about the pipe racks? What is the access to these locations? Because wherever you have tanks, you have pipes, and we need to consider any hindrance due to overhead pipes or underground pipelines while considering the design aspect of these projects. As you see in the lower bottom side, there is series of pipe above ground pipes. So now what is next? You know what needs from the design side. As a geotechnical engineer and structural engineer, what do we need to obtain in order to design a proper foundation system for these tanks? As these tanks are getting larger, the geotechnical exploration scope also need to cover the footprint of the tank. I'll tell you a fun fact about these tanks. I When I was working in a refinery on few projects, a guy told me that it takes up to 3 days to paint these tank structures. So imagine 300-foot diameter, 60-foot tall tank. So even if there is any dredge spoils in 50 feet of the area, and if there is no soil information or boring, that can cause problems. We really need to have a good coverage. We need to understand the site history of this thing, and that's why performing borings are essential or very primary thing we need to do. It's worth investing that much money to get the information instead of just relying on the adjacent tanks, where most of the time we've been told that okay, there are these tanks, just design this tank as well. But getting the soil information is one of the critical aspect in the design of the proper foundation system. We typically recommend performing 3 to 4 borings in the tank footprint area. Um, Again, the borings, number of borings is also dependent upon how much information we have available with us. What is the footprint size of the tank, the geology, and the site history. Typically, one boring or CPT sounding is performed to deeper depth to get the compressibility characteristic of the underlying soils. Once the borings are performed, The soil samples are brought into the laboratory for lab testing, the index property testing. Some of the typical testing performed are moisture content, Atterberg limits, and grain size. This test provides us the soil profile as with the depth. For example, if moisture content is close to the liquid limit of the soil, it tells us these soils are either normally consolidated or slightly over consolidated, and with the applied load, they will undergo excessive settlement or deformations. We can also perform additional testing such as consolidation testing to understand the pre-consolidation pressure and overall behavior of the soil when it will be subjected to the tank pressures. So in last few slides, we learned about design considerations. We learned about what do we need to obtain from the field in order to design a proper foundation system. Now, how do we design foundation systems? So industry, there are two options, shallow foundations and deep foundations. And in a minute, we'll talk about pros and cons of each of these systems. This picture is showing a snapshot of what is done in the industry. So if you have good soils, we can support the tank on the good soil, provided we can meet the performance criteria of the structure. But it's extremely difficult to find a good site nowadays. So you have two options left. One is shallow foundations, deep foundations. Shallow foundations. Yes, you have local equipment and contractors available to perform, to basically over excavate the soft, wet, saturated, or undocumented fill and replace that with structural fill. But question comes is oftentimes the sites are contaminated, so you can't really over excavate easily as it would be for a building. And second thing is these tanks are larger in diameter. So think about excavating about 5 feet of soil under 200 feet diameter tank. It's a massive earthwork. You also, depending upon the adjacent construction, you might need shoring. As I mentioned previously, if groundwater is shallow, you can perform the over excavation activity without having dewatering pumps. When if it's a rainy weather, the material is wet, everything is stopped. You really can't perform this activity. Also applies to the structural fill. If it's wet, you can get compaction of the wet material. Also, by doing all these studies, all these explorations, and performing the over excavation, the structural fill, will it provide the adequate bearing capacity you're looking for? Sometimes not. Second option is deep foundations, where the shallow foundations are not easy to construct. Some of the tanks can be supported on deep foundation. Although deep foundations can provide an excellent control for the settlement, as the piles and the pile caps, they carry the tank load all the way to deeper depths. Deep foundations are often very expensive. You need larger equipment. You also need to construct pile caps and structural slab. And also, if you have deep foundations like open-ended pipe piles or steel edge piles, often the welding is involved. If you have precast section, you need splicing. So all taken into all this consideration, it add on tremendous burden on the job. So let's talk about, if ground improvement solution, what benefits it can add to support the tank foundation. Over a decade, ground improvement system, what you see as we also call as intermediate foundation system, it has really become a number one or preferred options for the tank owners. And the reasons for that is I will explain you in next couple of slides. One thing is you're improving the ground or you're reinforcing the ground under the tank footprint. So you're creating a uniform reinforced crust under the tank. It does not require any removal or replacement of the material. If there is a shallow groundwater, you can still perform your ground improvement system installation. You can still support the tank on the shallow foundation, and you can get the bearing capacity from 5,000 to 8,000 psf, even higher. It obviously minimizes the differential settlement between the center of the tank, edge of the tank, edge to edge, as well as the adjacent tanks supports, provided they are supported on the ground improvement systems. From the construction standpoint, it is easy from the equipment side to bring in the equipment and install the Geopier elements, which are nothing but columns of aggregate. You don't need any pile cap or grade beams. Since we can offer higher bearing capacity, you can reduce your footing sizes. Temporary shoring is not required as there is no undercutting required. And very fast installation. This is the number one benefit of using ground improvement system. We can install about 60 to 80 piers a day, and generally 20 to 40% cost saving uh, over the ground, over excavation and replacement costs. So think about it. If you have a 200 feet diameter tank and you have to over excavate about 5 foot soils, the calculate the volume of soil that need to be over excavated, volume of soil that need to be placed and compacted, because you're going to need more volume as you're going to compact the loosely placed material, versus the cost of installing Geopier. Oftentimes, it's about 40% reduction in the cost when you install Geopier foundation versus you have over excavation greater than 5 feet for these tank areas. And other benefit is you can install Geopiers without disturbing any adjacent functional or operational facility. This is a snapshot of the different technologies we offer. So we just went over the benefits of ground improvement system. So what Geopier system has to offer to the industry? We have several technologies, and these are a few of the technologies what you see in the picture. GP3 is on the right hand side, and then you have center one impact. We have rigid inclusions, which can go to deeper depth and transfer all the load to the firm strata. We have armor pack systems. Today we're going to discuss about few systems which are mostly used on the ground improvement side of the tank industry. um, what you see in the picture is on your left hand side is a GP3 system, which is we call drill and fill system. The middle one is called impact system. It is the displacement system. You see a hopper attached to a hollow mandrel, and on the right hand side you see an X1 system where a prefabricated edge beam with a shield attached to the bottom of this edge beam. Typical equipment setup of a Geopier foundation system. What you see is a Geopier drill or auger to drill a hole. In the middle and the third picture, you see a bevel shaped patented tamping foot, which we use to ram the aggregate in the hole. So the simple process is you excavate a cavity with Geopier auger. You dump open graded stone the bottom, and then you compact it. Once the bottom bulb is built, you use well graded stone, compact it in thin lift, and you build a dense column of aggregate. This is a typical Geopier drill and fill setup. Very simple operation process here. You have mobile crew of about 4 people, 3 machines. Rapid installation depending upon the length of these piers. We can install about 30 to 50 Geopier elements per day, and very safe and clean process. Typical diameter of GP3 or drill and fill techniques are about 24-inch and 30-inch, and the depth limitation is about 30 feet. Let's watch a video of GP3 installation technique. It's drilling out a volume of soft and problematic or contaminated soils, dumping open graded stone as a bottom lift and tamping it with specialty tool, then ramming aggregates into the cavity in thin lift. What's happening here is as you're ramming the aggregates, it's pre-stressing and pre-straining the adjacent matrix soils. So you see these bulbs getting expanded into the adjacent soil matrix, thereby increasing the lateral stresses in the matrix soil and also increasing the stiffness of the overall metric soil. And what it does is it increases the load carrying capacity of the geopier elements. Next slide, what you see in front of you is our impact construction. This is a displacement approach. And where do we need the displacement approach? So if you are if there are caving soils or shallow groundwater conditions, or let's say we don't want any spoils, so this technique can be used where the hollow mandrel with a hopper attached to it is driven down to the desired depth. The aggregate is fed from the top, which passes through the hollow mandrel to the bottom of the hole, and the mandrel is withdrawn and pushed down in specific stroke pattern about some 4 feet up and 2 feet down to compact the aggregates, and that's how the geopier element is built. It's a rapid installation technique. We can install about 40 to 100 piers a day. The diameter of these elements vary from 16-inch to 20-inch, and depth limitation is about 45 feet. This is my favorite picture. What it's showing is how does geopier element look like when it's installed in the ground. We can't when the installation is done, we perform a lot of quality control during the installation, and once the piers are installed, we run modulus testing just like ASTM D1143. But this picture is so cool that it shows how geopier look like, and we excavated this pier and took some pictures. So what you see is a densely packed aggregate column. This is not cemented or concrete. This is just the aggregates. And it's a dilation behavior of the aggregate. So when you're ramming the aggregate in thin lifts, the particles roll over for the shearing and they fuse together to create a very high friction angle of these elements. Every 2 feet or so you see some undulated shape. What it's telling you is we are dumping or placing the aggregate in 2 foot lifts and we are compacting that. We have performed a lot of research, and we also continue to do the same on different technologies, type of materials, and this is showing our results of construction. On the left hand side you see a direct shear test performed by Fox and Cowell in 1998. Y-axis is your shear stress and x-axis normal stress, and this direct shear test results show you that you can get up to 48 degrees, 49 to 52 degrees for well graded, poorly graded aggregate. Um, So overall, you get 48 degrees with when you use open graded stone and 52 degrees with well graded stone. We typically use about 42 to 45 degrees of friction angle in designing the Geopier foundation system. These are the direct results. So these elements are stiffer than the surrounding metric soil. It's improving your soil to certain degree, but at the same time, these elements are so stiff, they are about 10 to 40 times stiffer than the native soils. Installing the Geopier also induces the lateral pressure increase in the metric soil and thereby increases the frictional shear resistance of the soil. Soil reinforcement means no setup time for piers. You can construct uh, footings right after the piers are installed. These are simply a column of aggregate, so there is no setup time, no concrete involved. Let's talk about some design overview and methodology for the tank structures. These are the large diameter tank, and when you talk about the oil storage tanks or any material storage tanks, three things we need to consider. One is bearing capacity, number two, total settlement, and number three, differential settlement, which is further divided into center to edge, differential settlement, and settlement along the perimeter, or we can also call as a distortion of the tank. Bearing capacity. Since these tank floors are not rigid, the bearing capacity is typically controlled by the edge instability. So the edge shearing mode effectively is one of the way to analyze the edge shearing mode is by performing the edge stability. And we can use slope W or slide program developed by Rock Science to perform the edge stability. And in a minute, we'll talk about how the slope stability is performed using the composite shear strength parameter values. Again, it's showing the tank floor is flexible. So what you see, the slip surfaces, those are for rigid footings. This is a typical soil profile. It's showing the surcharge load applied by the tank. You have a granular pad, which is shown by the yellow color, and you have ring wall footing, which is shown below that sliding surface. The typical profile is stiff clay overlying the medium stiff clay, and at the bottom you have very stiff clay. Slope stability analysis was performed in unreinforced condition or as is condition, and you see the factor of safety is about 1.1. Typical acceptable factor of safety is 1.3. So it clearly says that there are some issues with the edge stability of this tank. So what can we do to improve the edge stability? We can install wrap elements to increase the composite shear strength parameter values and take advantage. These elements are generally installed under the footprint of the tank to take advantages of the increase in the overburden pressure. Same soil profile with design of the Geopier elements. What you see here in light green and olive green color are RAP 1, RAP 2, RAP 3, RAP 4, which is nothing but RAM aggregate pier, Geopier 1, 2, 3, and 4. And the, why their nomenclature is different is because you have two layers of soils. So your RAP 1 and RAP 2 are installed in stiff clay with and then in the lighter blue color is RAP 3 and RAP 4. And the difference is where you have ring wall foundation or edge stability is concerned, sometimes you need close piers to be installed in close spacing, and as you go inside the or interior of the tank, pier spacing can be widened. This is simply economics, and provided your settlement differential settlement criteria works out well. Once the Geopier system is installed, you run the slope stability analysis, and as you see, your factor of safety in this case is 1.6. So when tank pressure of 5000 psf is applied, the native soil factor of safety was 1.1. With Geopier system, you could increase the factor of safety to 1.6. A modulus test is performed to verify the design is adequate, and oftentimes hydroload test is performed in accordance with API 650. And one of the benefit of hydroload test is when you erect the tank and add water weight in phases, and you're basically applying that pressure what tank would see in its design life. Some of the settlement is already taken place. So that helps in overall design of these tanks. So you need to know if the hydroload testing will be performed or not. Irrespective of that, we perform the design to make sure the performance criteria of these tank structures are met. This is a picture of a tank, and below the tank, as you see, the settlement profile with the black thin line showing the more settlement at the center versus edge. The profile is you have soft soils in upper 20 feet or so, underlain by stiff soil. As these structures are larger in diameter, they also have some relaxed criteria to accept the settlement. So typically, we have seen that 3 to 6 inches of total settlement is acceptable. Differential settlement, it's the difference between, or basically the settlement of the tank at the center versus the settlement tank of the tank at the edge. And what you see here is the distortion where you see the settlement of the tank along the perimeter of this tank. So it needs to meet the tank manufacturer's criteria. We just learned about what are the different performance criteria with respect to settlement. And let's learn about how do we evaluate or estimate settlement of these large diameter tank structures when you're designing for when you're designing the ground improvement solutions for these tanks. So we perform settlement control or the settlement of the settlement calculation in two-layer approach. The the first layer is upper zone, which is nothing but the reinforced zone or the zone where the geopiers are installed, including the bottom bulb of the geopier. The lower zone is the soils underlying the tip of the geopiers. As you know, the stresses goes down to deeper depth. The settlement of the lower zone also has a good sizable number. So let's talk about how do we estimate the upper zone. So when you install geopiers in grid pattern, we can divide the pressure of the tank in cell areas. So if we are installing piers in 5 foot by 5 foot grid pattern, each element represents or carries the load acting on that 5 by 5 area, and it's nothing but a cell area. So spacing required of wrap elements can be calculated as square root of Q cell divided by Q, where Q cell is the capacity of the geopier element and Q is the stress or the pressure exerted by the tank. For example, if you have Q cell value of 100 kips and pressure from the tank is 4 ksf, your square root of 25 is 5. So you can install piers or design piers for 5 foot on center spacing. The settlement of the upper zone is calculated using Hooke's law, which is QIH over Q is again the pressure exerted by the tank. I is influence factor. Using Bosnick's theory, we can obtain the value of I, and H is nothing but the length of the geopier element. Ecomp is calculated as EGRA plus EM 1 minus RA. What is RA and EG means? EG is elasticity modulus of elasticity of the geopier elements. Ra is the area replacement ratio, which means how much volume of soil is removed and replaced with the aggregate. So Ra of 20% means about 20% of the soil is removed and replaced with the aggregates. Em is the metric soil E value. Selection of Q cell and EG are very important for these tank structures because these tanks can tolerate greater settlement. Unlike buildings where you have to design foundations for 1 inch, tanks can be designed for higher settlement values. So by designing proper values or selecting proper parameter values, it adds on to the economics of the overall project. Lower zone settlement, you can estimate the lower zone settlement using conventional methods. For sand, you can use Schwarzman approach or values provided by Schwarzman indirect relationship, or you can perform some lab testing, what you see in the picture, where you can perform UC testing, and or you can perform UU testing. Also, what you see in the right hand side is a console curve where E versus log pressure, or it could be void ratio versus log pressure, or strain based consolidation curve, and you can obtain the compressibility parameters to estimate your lower zone settlement, just like any other textbook approach. As you see in the picture, the lower zone goes to deeper depth. Like, so if your tank is 100 feet, your 2B approach, your lower zone extends to 200 feet. Generally, when you see the pressure increase of delta P is less than 10%, you can stop your settlement calculations, or if you have any hard layer rock, you can stop your settlement calculations. Lower zone settlement, even you design a Geopler system or it's a pile supported, lower zone settlement does extend to the stresses does extend to deeper depths. So lower zone settlement number is the same for Geopier and piles. So what is the add-on benefit here is the Geopier installation cost or design is way economical and cost efficient than any pile or rigid foundation system. Also, geopiers provide a uniform reinforced crest under the tank. So if you have under the 300-foot diameter tank, if you have soil conditions varying due to the undocumented fill, or you have native soils on one side and you have dredge fill on other side, they really provide geopier system provide a uniform crust. So it really controls the differential settlement of the tank. Granular pad. So typical design of ram aggregate pier also includes the design of a proper thickness of granular pad. What is the purpose of providing this granular pad? The number one is arching principle. Since geopier elements are much stiffer than the surrounding metric soil, the design is performed so that the pressure from the tanks is attracted to the geopier elements. So the thickness of the granular pad is designed such a way that the piers located in X feet on center spacing, the arching cone intersect at the bottom of these tank floor areas, so that all the load from the tank eventually will get attracted to individual geopier elements, and the only area between the geopier elements, that's a triangular portion of granular fill, which will be exerted to the metric soil, which is literally 2 feet or 3 feet of triangular weight of the granular fill in between the geopier elements. So you see diameter of the geopier element, beta is the angle of the arching. And how do we estimate or calculate the thickness of the granular part is simply S minus D tangent times beta over 2. And S is the spacing of the geopier element, D is the diameter of the elements. The second advantage of this granular pad is it's providing a cushion between the tank floor and the geopier element. So you don't have any hard spots right under the tank floor. If we can also add cement to geopier elements to increase the shearing strength if needed. We have different solutions and technologies to deal with individual project, or if there are any other performance criteria than the typical criteria, we can visit that project and customize a solution per the performance criteria for that project. So let's talk about the case histories. This is a tank farm project in Houston Fuel Oil Terminal. We supported 10 above ground storage tanks. Picture showing the location of the tank in Houston, Texas. These tanks were 100-foot in diameter and 56-foot tall. Each tank carrying capacity was 86,000 barrels. A typical soil profile for based on the borings performed in the area. As you see, under shear strength in upper 15 feet is on the order of 500 to 750 psf, which is less than 1 ksf, and below 15 feet you're into some medium stiff to very stiff material with under shear strength of about 1.2 to 3 ksf, typical Beaumont profile. Only thing is you have fill in there, and could be attributed to the existing plant renovation or mass grading operations performed in the past. We perform edge stability analysis in unreinforced condition, and then design our Geopier system and perform the stability analysis. Settlement were estimated based on the approach we covered in last 10 minutes, upper zone, lower zone. And we designed a Geopier system along the perimeter of this tank. So these tanks were all supported on granular fill, and the solution or the need for this project was to support the tank along the edge of the tank for the edge stability purposes. We installed 17-foot long piers, and then granular fill was placed 2 feet along the edge and 3 feet at the center of the tank. As any other project, we've always performed modulus tests to validate the design and to see the performance of the Geopier elements. So what you see on the x-axis is the Geopier stress, and y-axis is deflection. The design stress is about 22 ksf. The test is performed in accordance with ASTM 1140, which is the static mod test, and we observe the deflection. What you see on the top with the hollow square is telltale. So what telltale is, we also install bottom plate with a Dewey DAG bars attached to the bottom plate, and they're connected to the footing, where when the test load is applied, the deformation at the top of the piers are measured. Also, the deformation at the bottom of the piers are measured. So what the difference between the top and bottom is nothing but the compression of the pier elements. So as you see, we loaded the pier for 22 ksf is the design stress. We loaded the pier up to 37 ksf, which is 150% times the design stress. And even at 150%, the deflection what you see at the top of the pier is about zero point 0.6 inches, and deformation or deflection you observe in the bottom of the pier, which is the telltale, is less than 1/10 of an inch. So overall, about 400 to $700,000 of savings on the project. Reduce the construction period in 6 weeks, and we met the settlement criteria, 1 inch settlement criteria. Another project, case history number 2, which is Magellan Terminals. This site, we did some phase construction. In 2006, we 120 feet diameter tanks, and in 2012, 11 and 12, we supported tanks 2505 and 2507. So case the site number 1, which is Galena Park site, we supported 10 120 feet diameter tanks. We installed 3,000 elements at 30-inch diameter. The geopiers were designed at 6 to 6.5 feet on center, and the shaft lengths were 14 to 18 feet. Under normal circumstances, where you see this clay fill, which is highly variable in upper 12 feet, and the groundwater is just below the fill, the normal construction process or the design would have been removal of this 12 feet of material and replacing with the structural fill. When you consider the 10 tanks with 120 feet in diameter, the time period for this over excavation and removal and the cost associated with that, we could save a lot of money, time, and pretty much do the construction within the stipulated time, meet the project performance criteria by installing a proper Geopier foundation system. What you see on your right hand side is the pier layout, which is, and the bottom left hand side is showing you the construction of the when the piers were installed. The the criteria was 4-inch hydro test at the center and 2-inch at the edge. Hydroload test was performed on these tanks, and we had predicted about 3.5 inches. What you see on the lower red and blue line, the predicted settlement was about 3.5 inches, which is at the center of the tank. So x-axis is your distance from, and y-axis your settlement, and the actual measured settlement during the hydroload test, when the tanks are supported with Geopier foundations, is hardly 1.5 inches. Case history number 3, this project was performed in 2019 for Ineos Phenol tank. It was a 99 feet diameter, relatively smaller size diameter tank with respect to what we have seen in the past. Internal diameter was about 85 feet, and height of the tank was 61 feet. The the specific gravity of the material is 1.07, and pressure, a design pressure, was 4,100 psf. Settlement criteria provided to us was 5 to 6 inches at the center and edge 3 to 4 inches. Let's take a look at the soil profile for this tank area. 3 borings were performed within the tank footprint. Uh, Pretty much consistent information as you see from the soil profile. Um, you may not be able to read all the numbers. I apologize for that, but what you see on this red circles, this is pretty much weight of hammer, 1 blow count, 2 blow count, dredge fill material with very low shear strength. The upper clay in upper 7 feet is probably a desiccated crust, but really from anywhere between 7 to 17 feet, you have soft material. So we designed a 30-inch drill and fill solution for this project. We installed 415 Geopier elements. Another example of supporting ancillary structures, it's a project Sasol in Lake Charles. What you see are the job was originally designed for deep foundations, a lot of pipe racks, mat showing the different pressure contours. This is another project in Valero Eagleford Crude unit. The original design was for precast concrete piles, and we installed Geopier elements as shown by these small circles. Maximum settlement criteria was 1.5 inches. We installed about 2140 piers. And shaft lengths vary because of the softer soil profile and tight settlement criteria. We install piers pending the size of this each equipment pad and the pressure exerted on this pad. We the shaft length varied from 12 feet to 14 feet. Added lot of cost and schedule benefit to the team. So all these things we seen some ground above ground storage tank, and this is the only example which is case study number 4 for elevated water storage tank. Typical profile of a water storage tank, you see ring wall foundation embedded about 5 feet or so in below the ground. You see the outer diameter and the inner diameter, and clear spacing between the ring wall is about 7 feet dia. Um, Typical profile, a construction area of the same storage tank after we install the Geopier. What you see in gray color are the locations of individual Geopier elements. So we installed the piers from the existing ground surface, and then contractor followed us. He over excavated the area. Minor grading was performed, and then you're ready to cast reinforcement and footings for to support this tank structure. The capacity of the tank is about 250,000 gallons. Service load designed for is 5,000 psf, and the soil profile what we seen earlier is clay sand, sandy fat clay profile. So this is the right hand side. You see the Geopier elements. Only 45 drill and fill elements were installed in a less than a day. The criteria was 2 inches total settlement and 1 inch of differential settlement. We just have to design elements 8 foot long, and we could offer a higher bearing capacity to the tank manufacturer. So with that, we will cover the last slide, which is summary of what we discussed in last 55 minutes. We have Geopier, we have several technologies to meet the project needs and your design criteria, depending on the soil conditions, not only in North America, but anywhere from Africa, Asia Pacific, or Australia, New Zealand, we can support your structures on ground improvement systems. We have experience of over 25 years. We perform a lot of quality control, QC, QA tests during the installation, after the installation to validate our design. We have done hundreds of successful tank farms over the last 2 decades. Please reach out to our REs. We have a lot of people behind the scene who are working days on these projects, and we're happy to help you. So if you have any need, please let us know. We have design build capabilities, which means we can, from the lead generation all the way to design, submitting the package, signing, sealing, the entire Geopier design is done in house. And most important thing is experience and our brand. So we are here for you. Please let us know if you have any project needs. We're happy to help you. Thank you for joining my webinar today.